This filament has been specifically developed to 3D print basketballs. The material is based on PLA and promises several exciting properties such as particularly high resilience, which I will test in this video. I also printed a full-size airless basketball so that I can compare it to a real ball. So stay tuned here at JanTec Engineering. It may sound a bit strange at first, and you might wonder why you would want to 3D print basketballs. The trend was started by Wilson when they introduced their Airless Gen 1, a basketball that does not need to be inflated and consists of a 3D printed lattice structure. Since the original was a limited edition and cost $2,500, some people in the DIY 3D printing community tried to 3D print their own ball at home. Many failed, especially with materials such as PLA, PETG or TPU. We will find out later why this was the case. The company Biqu, known for 3D printer accessories, has therefore developed a special filament for exactly this purpose. PLA-HR, where the HR stands for high resilience. Resilience in the context of materials science is defined by Wikipedia as the ability of a material to absorb energy when it is deformed elastically and release that energy upon unloading. 1 kilogram currently costs $59 in a Biqu shop, and at a density of 1.15 grams per cubic centimeter, this results in a price of 16 cents per meter. The filament is currently available in blue and orange, as well as black and white. When unpacking the spool, I noticed that the filament feels much more flexible than you're used to with PLA. It feels more like a TPU. By the way, Biqu did not sponsor this video and only provided one spool for free. The first question that arises is, which properties must the material have to be suitable for an airless basketball? On the one hand, it must be able to withstand impact loads and, in the best case, should also be able to bounce, meaning that it returns the impact energy instead of absorbing it. Two properties are of great importance for this: the resilience I already mentioned and impact strength. In addition, the optimal airless basketball filament should have good layer adhesion, since the mesh consists of a relatively thin connections that tend to be a weak point and break very easily. With this knowledge, it is also relatively easy to explain why materials such as unmodified PLA, ASA or TPU are unsuitable. PLA, for example, is stiff and brittle, which means that it suddenly breaks when it bounces on the floor. Although ASA has a higher impact strength, it usually has significantly poorer layer adhesion. Regular TPU is too soft and absorbs too much energy. Even though a ball made of TPU would probably not break, it would only bounce very low, if at all. We will find out in a moment whether PLA-HR from Biqu fulfills these properties. At this point, I would very briefly like to thank my first two channel members for supporting my work. But now let's move on to printing with the filament. Therefore, I loaded it into the Prusa XL and entered the temperatures from the spool and the slicer. First, I wanted to print my standard test specimens for the mechanical tests. My first attempt was on the satin sheet, where the prints came off after a very short time. This surprised me, as I've never had problems with normal PLA on the surface before. Then I applied a thin layer of Vision Miner nano adhesive, but this only made the adhesion worse. So I switched to the textured PI sheet. After a few fails, the parts finally stuck to it, but I didn't want to risk a longer print. That's why I took the third and last sheet, smooth PI. Here the material stuck very well, unfortunately too well. The prints were almost impossible to remove, causing me to destroy part of the PI. The behavior reminded me very much of TPU, with which I had similar experiences. So I gave it one last try: smooth PI with glue stick. The glue layer ensures that the print can be easily removed after cooling. In fact, this worked perfectly. I did a few more test prints with this method, like this mini Airless basketball. Because of the stringing, I decided to try the filament in my Sunlu S4. At this point, I would like to briefly mention that this is not what a customer experience should look like. I'm used to trying out more difficult filaments and also experiencing failures, but especially for beginners, this can be frustrating. When talking to Maurizio from the German YouTube channel mpox.de, I learned that he had similar issues with the filament on his Bambu Lab printers. That's why we shared our experiences with Biqu. As a result, they did further testing and finally adjusted the recommended print settings on their website. By the way, my damaged Prusa XL sheet will be replaced by them. My conclusion on printing: the material is definitely printable and, with the right setup, also reliable. Make sure to read the instructions on the website. Now to the mechanical properties, which I've determined using my DIY testing equipment. The impact strength can be analyzed using this test setup, in which a notched sample is smashed by a swinging hammer. Regular PLA is quite brittle, so the hammer is only slowed down a little. With PLA-HR, it's different. The material is so tough that it cannot be smashed. The sample absorbs the entire potential energy of the hammer, stopping it from swinging. With my 3-point bending test, the bending modulus can be calculated as a measure of stiffness. Normal PLA has a bending modulus of around 3 gigapascals, which is comparatively high. The high resilience PLA, on the other hand, is so flexible that it slides straight out of the measuring range of my dial indicator. I would therefore estimate the bending modulus to be below 400 megapascals. More important is the layer adhesion, which can be examined with a tensile test. Since I'm currently rebuilding my motorized test stand, I had to rely on the old one with a hand crank. Here I came up with an average tensile strength of 20.3 megapascals, which is slightly worse than normal PLA, but better than materials such as ASA. When I asked myself how to measure and compare resilience, I remembered a recent video from CNC Kitchen in which Stefan used such balls. So I printed a sphere with a diameter of 40 millimeters and 15% gyrate infill from the PLA-HR and built a similar test stand. The sphere is dropped from a height of 80 centimeters onto a concrete slab. After 3 tests, I calculated an average absorbed energy of 35% on the first impact. Compared to Stefan's results with various TPU and TPE filaments, this is quite good, and only Peba and Fiberflex 30D were able to absorb even less energy. Before we get to printing the Airless basketball, let me show you this. It's a full-color resin model of a human liver, 3D printed using JLC 3DP's WJP technology. The vibrant colors and smooth surface finish, thanks to their oil spraying technique, make it not just visually stunning, but also perfect for educational or professional use. JLC 3DP makes it easy. Upload your 3D models to their streamlined online platform, get an instant quote, and enjoy real-time order tracking. With production times as fast as 24 hours and delivery in just 2 days, they are perfect for tight deadlines. Whether you're printing medical models, prototypes, or creative projects, JLC 3DP ensures the highest quality. Plus, as a new user, you can get up to $60 in coupons at the link below. So, unleash your creativity and maybe create something even cooler than an Alice basketball. Huge thanks to JLC 3DP for sponsoring this part of the video. Now let's print the Alice basketball. There are various designs available online, with the designer Party Lime on printables particularly catching my eye. Biqu sent me a free MF file, but I didn't use it. Instead, I downloaded the Airless Basketball Gen 13 as an STL file and sliced it myself using the default settings. I only changed the nozzle to the recommended 0.6 mm. Since I didn't have one directly for the extruder in the XL, I used the V6 adapter with a normal 0.6 mm E3D nozzle. Installation was easy and straightforward. The print worked perfectly, and after about 3 days, I was able to remove my finished ball from the print bed. Thanks to the glue stick, this was also very easy. The ball has some stringing and visible layer lines due to the 0.6mm nozzle. Nevertheless, I'm satisfied with the finished results in terms of appearance. Removing the support structures was also surprisingly easy. The supports could be broken off in one piece without much effort. This would be much more difficult with materials such as TPU or PP. The finished ball weighs 567 grams, the support another 50 grams, so the print took 670 grams in total. A real air-filled basketball weighs 560 to 650 grams according to Wikipedia. My ball here is 588 grams. In this aspect, the two balls are very similar. At $59 per kilogram and a print time of 60 hours with an estimated power consumption of 120 watts and an electricity price of 35 cents per kilowatt hour, one ball costs me about $40. This price neglects the little time spent and the maintenance on the printer. The ball feels hard and, unlike my small test model, cannot be bent. At first, the bouncing is a bit unusual because you don't expect, let's call it a piece of plastic, to bounce that high. Overall, the bouncing behavior is very similar to a conventional ball, even if it bounces slightly less high. I also took the ball to a court, and the throws feel relatively natural. I noticed that the printed ball is quieter. The typical bouncing sound is duller and not as loud, especially outside on concrete. I bounced the ball around for several weeks and so far it is holding up without damage. But is it really worth printing this ball? Not so much financially, but if you want a functional airless basketball, this filament is definitely the right choice. The ball is also a cool eye catcher and shows what 3D printing is capable of. Now I would like to take a brief look at other possible applications for PLA-HR. As confirmed by the mechanical tests, the filament is particularly impact resistant. It is therefore also suitable for housings or external parts on a quadcopter, for example. Furthermore, customized shoe soles could be considered since the material is not as stiff as regular PLA, which was shown by the bending test. If you really want a basketball like this, then the filament definitely makes sense. If you follow my tips and those of the manufacturer, the print should work without any problems. But what do you think of the filament and what else could you use it for besides basketballs? Let me know in the comments. Thanks for watching, I really hope you enjoyed this video. Here you can subscribe to my channel and watch other exciting videos.